turn to Harry Nussbaumer, who is an astronomer at the Institute of Astronomy at the ETH in Zurich, and he has written a book, jointly authored, on discovering the expansion of the universe. So, over to you.
Thank you. Modern, with the emphasis on modern cosmology was started in 1917.
Stick to the microphone closely.
Well, can you hear me at the back?
Yeah.
Okay. So modern cosmology was really started in 1917. In 1915 and 16, Einstein had published his theory on general relativity. And in 1917, he applied it to cosmology in that paper here. And here you have the fundamental relation of general relativity. Now, I don't want to dig into those. In ordinary words, you might say that with these formulae, if you know what the universe looks like today, you can calculate what it will look like tomorrow. But it's important, you have to know, if you want to know how it looks like tomorrow, you have to know what it looks like today. Or mathematically, you have to know the boundary or the initial condition. And in order to apply this formula to cosmology, Einstein used common sense. He said, look, the universe is about, that's what astronomers tell me anyway, everywhere the same, has to be homogeneous. In addition, the old Greeks saw the same sky as we see today, so the universe has to be static. It mustn't change. Okay, in order to get such a static universe, he had to introduce this famous lambda, the cosmological constant. And when he did that, he obtained a universe, a static universe, and a homogeneous universe. Now, if you want to build a house, you go to an architect and you ask the architect, please draw me a plan of the house. A plan means the architect projects the three-dimensional house onto two dimensions of the plane. And you can do the same now with Einstein's solution. Einstein had the solution of a three-dimensional space, a closed space. And if you project that into one dimension, it's a circle, homogeneous, it's everywhere the same, everywhere the same. And in time, it doesn't change, it just moves upwards. So that's Einstein's cylindrical universe. Not very exciting, except that, of course, for conception, it's a bit strange that universe, you know, that curves, that comes back to you in itself. But anyway, that's Einstein's cylindrical universe. A few months, I started, okay. A few months later, De Sitter came up with a competing universe, a competing model. De Sitter went even further into simplifications. He said, well, let's look at an empty universe. How will that evolve? This is not as ridiculous as it may sound at the first go, because the density in the universe, the number of stars or of galaxy, is so low that as a first approximation you could just as well say there is nothing in it. Now, the fascinating and intriguing property of that De Sitter universe was that if into this empty universe, that came much later, but these are the two figures, De Sitter and Einstein, if into this empty universe you put two bodies, say we the observers and the observed one, up in New York or over in Andromeda, then the thing was that time was running differently at the two places. The further time runs fastest at the place of the observer. And the further you go away, the slower time is running. And De Sitter's paper was published in Monthly Notices, a long paper about 25 pages, and at the very end, De Sitter points out that actually there was a possibility of verifying that observationally, because if time was running slower at far distances, then if a chunk of matter was emitting a spectrum, that spectrum would be redshifted relative to the spectrum if the chunk of matter was emitting the spectrum at the place of the observer. And he pointed out to Eddington, who just before had published an annual review, also monthly notices, and Eddington mentioned 3 spiral nebulae, one Andromeda, which had a large blue shift, and 2 galaxies which had large redshifts. And they said, look, these large redshifts, they could support my model. And it was then that the theoreticians started to argue. There was big discussions, but only among theoreticians. Observers didn't bother. They sit there, Einstein, Weil, Klein, Eddington. What the hell does this mean, this de Sitter universe? And of course, it wouldn't have been discussed if it hadn't been for these redshifts, and they were from Slipher. So here Slipher was exceedingly important in that he provided these large wavelength shifts, these redshifts, where de Sitter could say, hey, they seem to support my model. Okay, so that was this huge discussion among the theoreticians, and it only changed in 1923 when Eddington published his book on general relativity. This book was very theoretical, but there was a fish hook in there for the observers. It was that table, we have seen it before, well, you don't see it here, but you have seen it before. In Eddington's book, there were 41 spiral nebulae with their wavelength shifts, and only 4 were blue shifted, all the others were red shifted. And Eddington pointed that out. He said, look, well, he didn't give that formula, but he gave all the preliminaries, and you easily can get that formula. He said, the further you are away, and that's the law, the more you should get wavelength shifts. And he said, this would be a support, if that is really true, that would strongly support de Sitter's universe. Okay, on that, the observers started to jump on the bandwagon. Wirtz wanted, he was a German astronomer, but highly interested in theory, and he knew theory. And he had then, I think, 42 nebulae, and so he wanted to see whether there was really such a relation between distance and velocity. And he knew distances were so uncertain. He said, but if I assume that all the nebulae are the same, then of course their apparent diameter gives me an indication of relative distances. Because of the uncertainties, he didn't take all the individual 42, but he grouped them into 6 different groups. And this is then the diameter, log the diameter, and that's the velocity shift. And you see, the smaller the nebula gets, the larger the shift. So he says, okay, fine. And he got a relationship, a logarithmic. Velocity is dependent on distance, and the further the distance, the larger the velocity. But he said, this is very provisional. This is preliminary, because the big uncertainties. However, what is not preliminary, he said, that's the conclusion. There remains no doubt velocities increase strongly with distance, as predicted by de Sitter. Okay, a very strong support. And when Wirtz did that, they always use Slipher's redshifts, or just wavelength shift, because there are also a few blue shifts. There were others, like Silberstein. Oh, yes, one point. If we discuss these papers, we always have to remember what the status of the knowledge was at that time. Shapley in 1918 had looked at the structure of the Milky Way. And contrary to the belief that actually came from the time of Herschel, Herschel had placed the Sun close to the center of the Milky Way. And Herschel sharply showed that this was not the case. With the globular cluster, he said there's something spherically symmetrical, and the place of the Sun is rather far away. But what interests us here is he places the spiral nebulae at the outer confines of the Milky Way. And it was already mentioned that Shapley vastly overestimated the size of the Milky Way. He didn't know about the absorbing power of the interstellar matter. And he thought that it was a long way for Shapley to arrive at these conclusions. The Milky Way, with its surrounding, that's the universe. And the spiral nebulae, they were somewhere outside, at the edge, but not something special. And you know probably all about the big debate where Curtis was of a different opinion. No, spiral nebulae, they are well, island universes. And Slipher in 1917, you have heard from Smith that Slipher in 1970, he thought, well, they are island universes. They are something special because of their large velocity shifts. Now, the others who jumped on the bandwagon, they were, for example, Silberstein, Lundmark, Stromgren, and we have to add Hubble. Silberstein had derived from De Sitter's work a formula that gave him a relation between the wavelength shift, the distance, and R, the radius of curvature, thus the size of the universe. And whereas Wirtz wanted just to prove that De Sitter could be right, that there was velocity-distance relation, these now, they wanted to derive the size of the universe. The formula was immediately criticized by Eddington, who thought that was wrong, and also by Lemaitre, who thought that's wrong. Both of them said there is no way of arriving from De Sitter to a negative sign. And when you look at Silberstein's work, he doesn't show us how he derived the formula. Okay, and Silberstein immediately said, okay, now I derive the radius of curvature, the size of the universe. He took globular clusters and spiral nebulae all in one pot and derived the size of the universe. It's about 30 megaparsec. He was immediately criticized by Lundmark, who said, oh no, look, what Silberstein does, it's not permissible, because he just picks out those objects which suit his theory or his prejudices. And then Lundmark said, we have to do it differently. And Lundmark looked at the O stars, you know, they want to derive cosmology from the O stars, from globular clusters, from Norway, and also from spiral nebulae. And here we have the first published Hubble diagram. It also carries the name of Hubble. Well, it was Lundmark, where you get the distance and the velocity. And Lundmark arrived at the conclusion, from the data we have available, you can't do cosmology. Lundmark, when you go through the paper, you see that he didn't doubt De Sitter. He thought De Sitter was probably right, but he said, the object we are working with, they are too close, you can't do cosmology with them. For example, for the O stars, the Cepheid, the globular clusters, he got contradictorily. He said, no way. And for the spiral nebulae, he said, well, you can't conclude anything from this. So the data are not of sufficient quality. Then we should add to this one Hubble. Hubble, in his famous 1929 paper, what did he want to do? You see, when you go through Hubble's paper of 1929, you see a clear break. They're about 3/4 through where he suddenly changed the emphasis. He investigates the solar motion against the background of the spiral nebulae. He thinks that's a lovely grid where I can trace the solar motion. And then you suddenly see that, hey, now he starts to put something different. He now goes to the relation between velocity of the nebulae and their distances. What had happened was that he had gone to Europe, to Leiden, because there was an international astronomical meeting in 1928. And there he must have learned that the work of Lundmark, which he certainly knew, it was published in monthly notices, that this was not just an individual astronomer's pastime, but it was a generally discussed problem, these velocities and the theory of de Sitter, that it had cosmological consequences. And then you see that Hubble, when he comes back in the last part, he now looks at this relation, where he then finds this relationship, which he says is preliminary. It's a linear, but it's preliminary. We have to have more observations. And then he says, he goes then for the interpretation, after he has found that relationship, and says, the outstanding feature, however, is the possibility that the velocity-distance relation may represent the de Sitter effect, and hence that the numerical data may be introduced into discussions of the general curvature of space. Now, I guess most of you know it, but for those who don't know, I want to repeat it here. There is not a single word in Hubble's paper about an expanding universe. That was projected onto him later on. Not a single word. That's everything in interpretation. He doesn't do any interpretation. Also in later works, he said the interpretation will leave to the theoreticians. But let's leave that now and go to the question, why the hell did de Sitter get redshifts? Einstein didn't. Okay. So we have to go back to general relativity. From these equations, what you want to get out are really the small g's. That's the metric. The metric that gives you the geometrical structure of the universe. And you then get the line element, which, for example, for a beam of light, see here, gives you the relationship between the velocity. Well, for a beam of light, how much time does it take to traverse a distance dr? It's the normal, simple motorway relationship. The velocity times the time you are driving gives you the distance you have gone through. And the important point here with Einstein's relationship is that it is valid for every point in the universe, everywhere. And with Einstein, even for all times past and future. This is quite different for de Sitter. You also have C times dt equals dr, but now there is a coefficient. And this coefficient depends on the distance between you, the one who studies the object, and the observed one. And here, Lemaitre sets in. Lemaitre criticizes that. Lemaitre says, that's forbidden, you mustn't do that, that's a deadly sin. So, de Sitter committed a deadly sin. What's the deadly sin? Well, he sins against one of the fundamental principles of our cosmology, that's homogeneity. That means complete democracy. Everywhere in the universe, you mustn't single out some point and give him different laws. And that's what de Sitter does. The observer has a different time than the observed. Time is run differently. You mustn't do that. Lemaitre criticized that in his first paper, 1925, where he saw that there was something wrong with de Sitter, and he pointed out, this is wrong, you mustn't do that. And Then in 1927, Lemaitre got back to the fundamental equations of general relativity, and he studied them. And now, he made the same discovery that Friedman had already made in 1922. He discovered that these equations have not only as solutions the static universe of Einstein and de Sitter, but they allow a dynamic universe that could be expanding or contracting, pulsating. And he says, ah, great, great. And now, of course, what's these stand redshifts? What's these stand redshifts? Lemaitre then also says we can go back to Einstein's solution. Einstein's solution for the line element was this one here. Put this as 1. Then you have the velocity times distance equals times time is the distance that has gone through. But now you mustn't, or we don't need to postulate that the universe stays the same. It's a dynamic universe. And then this factor here comes in and changes with time. And so you could have an expanding universe or a contracting, but theory doesn't tell you which one it is. Observations have to show us. And okay, up to here, well, Friedman didn't do that kind of thing. Not because he was not interested in astronomy or observations, but they simply were not available. Whereas Lemaitre already, he knew his observations. He had been to Eddington to study theory. He had been to Shapley over there for 1 year, so he knew what observations were, and he now included that. And he said, okay, the redshifts, they show us that, well, here we have actually Lemaitre's universe. You also have that circle, as you had with Einstein, but now, contrary to Einstein, de Sitter, if you sit anywhere on this point, the structure, the little g's are the same. They are the same everywhere, and if you now move in time, everyone moves along a geodesic. And the radius of curvature, which would go through here, is different up here than down there. And this changes the redshift. And if you increase the radius of curvature, it means you get a redshift. If you decrease the radius of curvature, you would get a blue shift. And so say, okay, now he refers to observations. He doesn't cite Lemaitre. He doesn't cite Slipher. He cites Stromberg. Stromberg, on the other hand, cites Slipher. And Stromberg got the redshifts from Eddington, from this table, and added 2 more. So that's what Lemaitre took as observations. As observations, he had, on the one hand, distances, he needed distances. Those he got from Hubble. And it's not 23, it's 1925 that Hubble actually published the first one. It's important. These 2 years make a difference here. Then he published magnitudes and a relationship between magnitude and distance. So Lemaitre used that to get the distances, and he used Slipher's redshifts. But he was aware, well, there were 2 things. He had first of all to know, is it redshift or blue shift? He knew it's redshift, so we must be in an expanding universe. Then he derived for when the object you observe is not too far away, he derived this linear relationship in 1927, which we now call the Hubble relation, but it was really Lemaitre who discovered it theoretically. And he said, oh, would be lovely if he could verify whether it's linear. But he soon realized we can't do that. The observations are too uncertain. So he said, we have to leave it to a future generation, or just to the future for the astronomers, to verify the linearity of that relationship there. But he said, I can always calculate the coefficient of expansion, the h up there. How did he do it? Well, he simply took all the distances, took the mean value, took all the velocities, took the mean value, and then he had his age, and he got 575 kilometers per second per megaparsec. This is published in the 1927 paper. It was cut out in the translation, the English translation. The derivation of that was cut out. And this is Hubble's diagram, and Lemaitre didn't draw such a diagram. That was done a few years ago by Dürbeck, who simply took all the observations that Lemaitre had used and had put it in here. And so you can see that Lemaitre was right to say, well, I can't prove with that the linearity, I can't prove with these observations the linearity. So now if Hubble had known about Lemaitre, he could have said, I have verified Lemaitre's prediction of a linear relationship. But Hubble didn't know about Lemaitre. Can't blame him for that. Anyway, when Hubble did the same thing as Lemaitre, Hubble also knew that there was big uncertainties. So he also took the mean of all the distances and the mean of all the velocities, and he got 530 instead of 575. So you see the same. And that's not astonishing, because Hubble used the same data as Lemaitre did, only he didn't give any references. So that later on gave the impression as if the velocities had also come from him, but he gave the numbers, and when you compare the number, you see that they are 1-to-1 from Eddington's table. And then Hubble went on and said, okay, now don't take the mean, I take the best data. So he reduced it from this 41 to I think about 20 or so, such high quality, what he called it. Then he got 500, which is still the same. Which is still the same. So, okay, how did things go on? Well, Relativity will tell us about the discovery of the expanding universe. I don't want to dig into that now. Lemaitre published that in Annales de la Société Bruxelles, de la Société Scientifique de Bruxelles, in French, so his chance of being read were practically down to zero. But then it was discovered later on. Well, it was discovered when Decatur went to London after the publication of Hubble. He went. Am I overshooting? Not yet.
You're getting close.
I'm getting close. Okay. In that case, anyway, then followed this was discovery of the expanding universe by Lemaitre. Lemaitre knew he was discovering the expanding universe. It was not something that was projected onto him later on. He stated that. And it was not just galaxies running away, but space expanding. At the time of his discovery, Lemaitre didn't know about Friedman. Because when Lemaitre had made his discovery, he showed it to Einstein, who was there at the Solvay Congress. And Einstein said, nothing wrong with the formalism, but it's abominable physics. He had said the same to Friedman many years ago. And then Einstein pointed out to Lemaitre that Friedman had done something similar before, anyway on the formalism, not on the astronomy. And from that moved onward, Lemaitre always cited Friedman. So he was absolutely correct and a real gentleman. He didn't appropriate this discovery of the formalism for himself. But anyway, that went then on, and of course there came then the big discussion. Lemaitre and de Sitter were enthusiastic when they learned about this. Finally, we have found a solution. But then, if we have an expanding universe, how the hell did it start? And that we will get. Who will talk about Eddington? You will talk about Eddington. You will certainly mention that discussion. There, Eddington and Lemaitre had completely different ideas, which we'll hear about tomorrow. No, this afternoon. And let me come back to the main point of this talk. The main point of this talk is, where did Slipher's redshifts come in? They came in at two decisive moments in the discovery of the expanding universe. First, when de Sitter had developed his theory, he could, just on 3 galaxies, he could point to Slipher's wavelength shift and say, there are observations that seem to support me, and they were Slipher's redshift, of course, blue shift. There are Slipher's redshifts, so that was very decisive. Without those observations, that discussion wouldn't have happened, because de Sitter's model was just a bit too crazy. But with the support that he could explain the observations, the discussion was going on. And again, he became crucial when Lemaitre had derived the formalism for the dynamic universe, and now wanted to take in the observations. He had to know, are they blue shifted or red shifted? Well, of course, Lemaitre knew they are red shifted, so the universe must be expanding. And then afterwards, that age, well, that's then secondary, but again, at that moment, Slipher's redshifts were all important. They showed the universe is expanding. So these were the two crucial points where Slipher's redshifts came in. Thank you.
All right, we can have a few questions. It's built in. We're running late, but that's because we started late. Sorry.
Yes, thank you for your lecture, and more importantly for your outstanding book. I have some problems with your interpretations. Now I will discuss only the one. You talked about Silberstein as if he made a mistake, and as if he didn't explain his formula and some of his data. And you refer to Lundmark, and if you read the paper by Lundmark, you see that Lundmark mentioned name of Silberstein 20 times.
Yes.
It means that he took a theory from Silberstein.
Yep.
And all the pictures, it is just repetition of what Silberstein said. It's one thing. Another, when you're saying that he didn't explain, you might refer to a paper, which Lundmark also referred, Silberstein published 1924. But in his book, published in 1924, Silberstein gave complete derivation of the formula with sign. And he corrected mistake by while, which put tangent there. So I don't know why you made this small.
Okay. Yes, Lundmark. Perhaps I didn't say clearly enough. Not only Silberstein used that formula by Silberstein, but also Lundmark and others took it. But the Lemaitre and Eddington reproached the derivation of Silberstein because they said there is no way of getting a negative sign.
There are root squares, and if you take
well,
square, then,
yes, they're root square, but that doesn't mean that when you come to physics that you are allowed to take both. Anyway, that's how it happened.
Let us discuss.
Yes.
Thanks, Harry, for a fantastic talk. And as Harry said,
I have to come close because the explosion cut off my hand and also cut off the right ear.
Thank you for a fantastic talk and a fantastic book, as Harry says. Both very important. One comment to the question. First of all, as an experimentalist, I take great comfort from the fact that it took 10 years for somebody to notice that the de Sitter universe might be homogeneous in space, but it's not homogeneous in space-time. But it's very curious, 10 whole years before, so it shows a picture of everybody groping for understanding. But on the same thing, here's my question. I call them the heroes, but those guys, Wirtz and Lundmark and Silberstein and all of them, who are trying to tie this new theory to experiment, like Hubble, in almost all those papers, they talk about the de Sitter effect singular. But as you said, there are two de Sitter effects.
Yep.
And I never really understand why are they so obsessed with a relation between velocity and distance, because if it was the time dilation effect, if that was the dominant effect, it would be velocity versus distance squared. So I've never really understood that. I've looked at the papers.
Yes, de Sitter he gave, from de Sitter you can have two effects. You have one effect which time is running slower at distances, and you have another effect which pushes particles away. So that's Eddington already said, well, that's not a static universe in that case, if the particles are being pushed away. And that, of course, gives then a kind of Doppler shifts, real Doppler shifts when they're running away. So you would have the real Doppler shift, and you would have the other effect. Time is running slower. But the theoreticians were already confused. When you read through these discussions, Hermann Weyl and all these people, no one could make head or tail out of it. So the observers certainly didn't want to complicate it. They knew there was a redshift. Hubble said, I find in the first approximation I can put it as linear, but it's preliminary because he probably had learned, Hubble was no theoretician, had learned that there could also be a quadratic effect. Well, there are two things. One, it was still the discussion that only with the end of 1925 or at the beginning of 25, when Hubble had shown the distances, extragalactic nature, they could have had it from Öpik, for example, for Andromeda, but okay, 1925 they got it. So finally, that was cleared. It was a confusing situation. So we mustn't be too strict on that.
Well, let's thank Harry for his paper and his